Welcome back to CST432 Microprocessors and Embedded Systems. Today we will learn what it means to dissect the beast. Now, as we shall see, robots can have various shapes and sizes depending on their function and design. So it is not possible to understand and analyze every single possible robot out there. Instead, we will study one example, which is a tribot, which is one of the common robots that is found with the LEGO MINDSTORMS kit. Now, the tribot is something that was developed with the first version of the retail kit from LEGO. However, if you're using the LEGO MINDSTORMS education set, it may not be possible to build the tribot exactly. So instead, we also have an alternative version that's built using the LEGO educational MINDSTORMS kit that performs a similar function to the tribot. And here in this slide, we can see the exploded view of the educational kit tribot. What are the components of tribot? We'll take an analogy for an anatomy. In any animal, we can group the functions into the central and peripheral nervous system, the skeletal framework, the sensors, the muscles, and finally, we also look at means of communications. So in the tribot, the central nervous system is actually the next brick, whereas the peripheral nervous system are the connector cables that transmit and receive the signals from the various sensors and motors. Now in the next MINDSTORMS, the skeletal framework consists of technic beams, joints and connectors that allow the robot to move as well as do various functions. Now the MINDSTORMS sensors are used to sense the environment as well as provide inputs to the robot, while the muscles are made out of servo motors and gears that drive the various limbs and other attachments of the robot. Finally, for communications, we have things like the speaker that generates audio or sound, Bluetooth that allows us to remotely communicate through the wireless interface, as well as the USB cable interface that allow us to connect to the computer for downloading and accessing the next itself. Now we're going to compare the MINDSTORMS sensors to human or biological sensors. Now the typical biological sensors that most animals have are touch, hearing, smell, sight, taste, balance and acceleration, temperature, pain, kinesthesia, direction, and echolocation. Now some of these may not be found in all animals or living things. However, the MINDSTORMS has some equivalent sensors such as a touch sensor, a sound sensor for measuring the intensity or loudness of sounds. Unfortunately, it cannot smell or taste, but it can detect light in terms of intensity as well as color, but these are found in two separate sensors. One is the light sensor, the other is the color sensor. In addition, to determine the position, balance, and acceleration, we have gyroscopes and accelerometers. And there are temperature sensors available, as well as being able to detect the position of a given limb or motor by using the servo mechanism on the motor itself. In addition, magnetometers can tell us the direction, and the ultrasound sensor provides a very primitive form of echolocation, such as that used by bats and other marine animals. Of course, we will focus our attention more on the next break because this is where you spend most of the time when we are learning about the processor and other issues of programming. The next break is the brain of the robot. It contains the Atmel AT91 SAM7S256 microcontroller. Don't worry about what the acronym means. But basically what it tells us is that it contains an ARM processor. It can execute native ARM object code directly. Otherwise, by default, it will simulate a virtual machine architecture for executing next bytecode or NBC executables using the default firmware Alternatively, if we install other firmwares, you can execute Java bytecode using LaHost as an example. To better understand the Atmel's microcontroller, we will first explore the design of microprocessors. Secondly, we will also examine the various blocks found in the microprocessor, and we will evaluate the impact of architectural decisions on processor performance. What are some of the main concepts we will learn in this lecture? First is, what's the difference between CISC versus RISC? Secondly, what is the memory architecture of a processor? And thirdly, what are instruction pipelines? As we are learning about these things, something to keep in mind, maybe you want to ask yourself, first, what is the effect of having a small number of registers on the CPU performance? Secondly, how does different memory and I/O architecture affect the performance of the system? And thirdly, what are the advantages and disadvantages of having instruction pipelines? Now, CISC versus RISC is something that has been debated over the past 20-30 years. But typically, a CISC processor or complex instruction set processor have large and variable instruction sets. They have small number of registers, they have a variety of data types supported natively by the processor, they have multiple memory access mechanisms, they have variable length instructions and operands, they have variable instruction execution timing, and typically, in order to support all these features, they need a large number of transistors. In contrast, RISC or reduced instruction set computer architectures have limited instruction sets. To compensate for this, they have a large number of registers, and they have limited number of data types to simplify the processing overheads, and they have limited memory access mechanisms compared to CISC processors. Fortunately, they have fixed length instructions and operands, and typically are based on the natural word length of the processor. This simplifies execution, and they are able to achieve fixed execution timing, typically single cycle instructions for most instructions. And because they have fixed instruction length and fixed operand sizes, the smaller number of transistors are needed to implement a given RISC processor. The excess transistor budget can be used for RAM or cache or other peripheral logic. We will first look at a typical CISC processor. The popular Intel processor architecture, the 32-bit architecture given here in this diagram, has 8 general purpose registers as well as 8 6-segment registers that are used for addressing locations in memory. And in addition, more recent Intel processors include a floating point unit which contains 8 floating point registers, and they are used in conjunction with 8 MMX registers that are used for programming multimedia applications. In contrast, a typical RISC processor, such as a PowerPC processor shown here in this diagram, have a large number of registers available to the user. Typically, there are 32 general purpose registers for integer arithmetic. In addition, there are another 32 floating point registers that can be used for floating point and other calculations. Now, another issue that affects the processor performance is the memory architecture. Memory architecture of a processor refers to how the storage locations, or RAM, or permanent storage such as flash and EEPROM is accessed from the microprocessor. The typical memory architecture is called the von Neumann architecture, which combines the location for storing instructions or code with the locations for storing data. So consequently, instruction and data are found in the same memory address space. On the other hand, the Harvard architecture separates the instruction address space from the data address space. This allows us to access the instructions and the data separately and simultaneously. However, the von Neumann architecture has a bottleneck. it has only one data and address bus, and sharing this data and address bus to access the memory locations for instructions as well as data will slow down the computational speed of or throughput of the processor. On the other hand, the hardware architecture is much more complicated. It requires two separate sets of data and address buses, and if you have all these components outside of this processor package, this will cause the device to contain many traces to support this dual bus architecture. A compromise called the modified hardware architecture has therefore been implemented, where the single address and data bus of the von Neumann architecture is maintained, but cache or extra memory locations inside the microprocessor is used to store the most frequently accessed instructions and data locations to avoid having to go through the actual address and data buses to main memory itself. This allows us to improve the throughput and the performance of the processor without incurring the additional lines and connections between the processor and memory. The input and output architecture of the processor is also important. The first is called the unified address space, which combines the access to peripheral devices and other I/O devices registers into the same address space as used for instructions and memory data. This simplifies the programming because you can use the same sets of instructions for accessing to data and to instruction address space to access the I/O registers. In contrast, some processors implement separated address spaces for I/O and memory storage. This allows us to use a separate set of instructions to access the I/O registers, but unfortunately also it limits the number of I/O registers that can be addressable, typically because the address space for I/O is limited. We will also study something called pipelining. Pipelining involves the execution of instructions in the processor in a staggered fashion. Now in the top example here, we see that instructions are taken or fetched from memory and then decoded to understand what the processor needs to do in response to the instruction, and finally executed to allow the instruction to take effect. Now if you consider a three-stage instruction fetch, decode and execute scheme, in 6 cycles we can only execute 2 instructions. For a processor that implements pipelining, we can stagger the execution of these instructions such that a fetch process occurs every instruction cycle, followed by a decode process, and finally the execute process. Because they are staggered, this allows us to execute 4 instructions in the same 6 cycles compared to the non-pipeline processor case. Here we will look at the components in a basic microprocessor in greater detail. On the bottom right, we have the external buses to interface to main memory. This includes the address bus, the data bus, as well as any interrupt and control logic for controlling peripherals. Once we retrieve the instruction from memory, it goes into the instruction pipeline, which is basically the fetch module of the processor. The instruction decoder then processes the instruction to determine what other variables or operands are used by the instruction. And finally, the instruction control unit will take the instruction and perform or command the arithmetic logic unit or ALU to perform the actual instruction, or whether it is addition, subtraction, division, or some other calculation needed. Now the ALU typically would take the inputs from the register file. Okay, the register file are dedicated memory locations inside the CPU that stores variables temporarily, and it is separate from the main memory. Having a large number of registers in the register file significantly reduces the need to access main memory for the data. Okay, finally, the results of any calculations are stored back in the register file, and the certain flags in the flag register are updated to indicate the result of the calculation. We can see similar features to our basic architecture diagram in the ARM processor architecture diagram here. This is the processor architecture diagram for the ARM7 TDMI processor, which is found in the Atmel processor microcontroller that we are interested in. On the right side, we have the I/O and other signals that are interfacing the controller to the external memory and peripherals. On the left hand side, we see the address register at the top, which is used to control access to the memory location that is storing the instructions that we want to execute. This feeds the register bank, which includes all the temporary variables that are used for the calculation by the instructions. And finally, at the bottom left, we have the arithmetic logic unit, which is the circuit that performs the actual computation or calculation using the variable values in the register file. Of course, there are processors with more advanced features. In this diagram, we see the modification or enhancement of the basic processor architecture to include things like a memory management unit or MMU that allows us to perform virtual memory access to physical memory. We have the caches, which improves the performance of the processor by providing a hybrid or von Neumann architecture processor with some hardware architecture features. Finally, we may have a longer pipeline that allows us to break down the instruction execution process into more steps. And we may have a branch prediction unit which is used to improve the performance of the processor. One of the limitations of a pipeline is that if there is a branch in control in the processor, it will force the processor to flush the pipeline in order to retrieve the information from a different location in memory. This stalls the processor and reduces the throughput of instructions. Having an intelligent branch processing unit overcomes some of these limitations and improves the throughput. Finally, advanced microprocessors may include multiple copies of the ALU or even additional dedicated processors such as the floating point unit or vector processors that performs dedicated tasks such as video and audio encoding and decoding. Now, advanced microprocessors may include multiple cores in the same die to improve the throughput and performance of the processor. We have come a long way since the beginning of microprocessors in the 70s. Today, we find that most processors are no longer purely CISC or RISC. Instead, we see a convergence. The RISC architecture has been adopted in the implementation of multiple CISC processors. The CISC instruction set is executed as micro operations on a RISC core. So strictly speaking, there are no pure RISC or pure CISC processors today. Instead, what we have are CISC instruction sets running on RISC processor cores, but you may not be able to see the RISC processor core on such architectures. Today, the focus is on efficiency of processing, measured as performance per watt or MIPS per watt, instead of purely the number of processors or number of transistors or the number of clock cycles or the speed of the processor. With that, I leave you with some additional questions to think about. First, what is the disadvantage of using a parallel data bus on computer system design? Okay. Secondly, what type of hardware mechanisms are needed to support multiple operating systems virtualization? And thirdly, what is the main performance bottleneck for multiple core CPUs? That's all. Thank you.